We're going to talk about KRaft, which is Kafka's new consensus mechanism that removes the need for ZooKeeper. We'll cover how KRaft works, its benefits, and why it simplifies Kafka architecture. So what exactly is KRaft? KRaft stands for Kafka Raft. It's a consensus algorithm that's built directly into Kafka, meaning we no longer need ZooKeeper for broker coordination. KRaft handles things like leader elections and replication natively within Kafka itself. This significantly simplifies Kafka architecture. Here is a diagram showing how KRaft replaces ZooKeeper and acts as a Kafka new coordination system. Let's move on to how KRaft actually works. KRaft uses the Raft consensus algorithm to coordinate leader election and replication directly between Kafka brokers. There's no need for an external system like ZooKeeper. This leader election process in KRaft is very similar to what ZooKeeper did, but it's more streamlined and fully integrated into Kafka. Brokers communicate with each other directly, and when one broker goes down, KRaft ensures that another broker takes over seamlessly. Now, why is KRaft such a big deal for Kafka? With KRaft, Kafka can manage its own metadata. This means you don't need a separate ZooKeeper cluster anymore. Kafka handles everything internally, making it more efficient and reducing operational overhead. By eliminating ZooKeeper, KRaft simplifies Kafka scalability, making it easier to run large-scale Kafka deployments. Let's walk through an example to see how KRaft acts as a coordination service. Now we have three brokers, broker 1, broker 2, and broker 3. KRaft is managing all of them. Each broker is sending a heartbeat to KRaft to indicate it's alive and functioning. But what happens if one of these brokers, say broker 1, stops sending its heartbeat? KRaft immediately notices this and initiates the leader election process. In our case, broker 2 gets elected as the new leader, and it starts handling the incoming client request. This ensures that Kafka remains available and operational, even though one of the brokers is down. Let's visualize this process with some diagrams. Here's the initial state where all brokers are online and sending heartbeats to KRaft. Now broker 1 stops responding. The other brokers detect the missed heartbeat from broker 1 and initiate the election process to determine the new leader. In this case, broker 2 has been selected to be the new leader. Once broker 2 is elected as the new leader, the client needs to connect to broker 2. This is typically done through a metadata refresh process, where the client discovers the available brokers. Let's visualize this process as a sequence of events. Imagine broker 1 suddenly stops sending its heartbeat, which signals that something is wrong. Both broker 2 and broker 3 detect the missed heartbeat, prompting them to check the heartbeat status and start the leader election process, step 3. Broker 2 is then elected as the new leader, step 4. When a client sends a request to broker 1, step 6, broker 1 is unresponsive, step 7. The client then requests metadata from broker 2, step 8, to find the new leader, and is directed to broker 2, step 9, for handling new requests, step 10. This ensures the cluster stays up and running without any disruption.